Hello, my name is Colin Riddell. I work with a company called QuickPlay Software, and I'm going to talk to you about OpenCL. I'm going to tell you about QuickPlay, some about OpenCL, and how we use OpenCL at QuickPlay. QuickPlay is a small company based in Scotland. We have 15 compiler engineers. We work with compilers. We started off in 2002 roughly, making CPU compilers, and we now work with making GPU-based compilers and compilers that target GPUs as well, and working with technology such as OpenGL and OpenCL. OpenCL and OpenGL Khronos standards are very prominent in all our technologies. This includes our game development research, our shading compiler optimizations, our OpenGL shader research, and OpenCL compute research as well. So all our technologies are very involved with OpenCL and OpenGL. Our two main technologies are a testing system and a compiler system for targeting CPU and GPU technologies. The testing system enables our engineers to regression test the compiler technology, and the offload compiler system was designed initially targeting the cell processor. We have now changed that technology to target OpenCL, and we use our technology with OpenCL to try it and make a C++ OpenCL implementation, which I'll explain shortly. Okay, I'm going to tell you some overview of OpenCL and some simple technical aspects of how OpenCL works. OpenCL uses the parallelism and power of a GPU or device such as DSP or FPGA to run compute units which are normally run on a CPU, moving on from the tasks that are computed normally on a CPU with homogeneous tools such as OpenMP, and it's also the next step on, and similar to GL, SL shaders used on GPUs. OpenCL can be broken up into three components. The first component on the OpenCL device is the device itself. The device can consist of more than one compute units, and the compute units can consist of more than one processing elements. Your device and the compute units and the processing elements are separate from the host. Usually the host is a CPU and the device is a GPU, but the device can be a DSP or an FPGA as well. The big idea behind OpenCL is to write a contained piece of code, like a shader, which runs compute tasks on the GPU or device, rather than domain-specific shaders for computing graphics. You define an n-dimensional computation domain within your OpenCL, and you define the kernel, which is the section of code on the right-hand side, to actually execute on the GPU or device. You can target many different types of device or hardware with OpenCL, ideally, as I mentioned, DSPs and FPGAs as well as GPUs. The example that I've given there, I'm trying to compare a simple regular compute task that we'd run on a host with something with the same program that executing on OpenCL. OpenCL is executed within an n-dimensional domain. So this means that it inherently has a loop built in. This is the way I think about it and understand it. Whereas on this helps exploit the parallelism behind the task, and it helps exploit the parallelism behind the task-driven object. On the left-hand side, under the section Traditional Loops, this is running on a CPU device. This will not give you any parallelism because it doesn't exploit the n-dimensional domain that OpenCL provides. OpenCL has a very strict memory model compared to that of the host devices such as CPU. It's broken up into three main areas of memory. The first of which is the most local part of memory, as we'd call it, and is called private memory. Private memory, objects stored in private memory cannot be shared between any other instances or executions or work items of the same kernel. The next step up from private memory is local memory. Local memory is very similar to private memory, but objects stored in local memory can be shared between instances or work items, as they're called in OpenCL, of the same kernel. This lets you parallelize your data across many kernels. So local memory is in most cases the preferred area of memory to store your objects. Global memory is visible to all of the work groups, or all kernel executions, even kernel executions of different types. The input and output data is passed in explicitly from the host. The host, as I mentioned, is normally a CPU, and the programmer has to very explicitly provide the data in from the CPU into the parameters of the kernel. This is a simple example of how some code might be represented and how that looks compared to the memory model. As I say, it's very explicit. The private memory is only available to the local kernel, the kernel that's currently being executed. The local memory can be used between kernels, and the global memory can be used between all kernels. On the host side for OpenCL, this is all of these APIs are provided by the Khronos specification, and I'm not going to go through every single one of them, but in order, these commands will let you set up a device and send data to the OpenCL device, wait for the data to come back, and read the data when it does. The most interesting that I will point out is CL create buffer. Under the heading it says allocate GPU in-out memory for buffers. This lets you actually send real data to the GPU or accelerator rather than simple primitive types such as floats or integers. This is the most commonly used for sending data to the GPU. I'll talk a little bit about OpenCL 1.2. It is the most current available specification of OpenCL 1.2. With OpenCL 1.2, you can add custom devices, and built-in kernels are also supported. There are some improvements in the image functionality. It lets you do something similar to that of shaders, but not all of the features, of course, with CL in queue fill buffer, and this lets you fill in some very simple colors and patterns similar to that you would create on a shader. You can 1D images are now supported, and 1D image arrays as well. With OpenCL 1.2, you can compile the many different types of kernels and then link them together. This wasn't previously available in OpenCL 1.1. And what that lets you do is write different kernels for different types of task. So you could have two kernels to do one particular task, and another two different type of kernel to do a different task. and then you can use the device partitioning that you get with OpenCL 1.2 to combine these processes. And as I say, that wasn't previously supported in 1.1, which is the slightly older version of the spec. So I'm going to tell you a little bit now about the company CodePlay and how we work with OpenCL. We are trying to use OpenCL as a backend for our compiler tools. What I mean by that is we're trying to take, parse and compile C++ on the front end of our compiler and output conformant OpenCL kernels that can then be compiled and used by a conformant OpenCL implementation, such as the NVIDIA implementation or an AMD implementation. We think this is a good approach to trying to push the future of OpenCL, because it can make acceleration easy on the GPU, because a higher level language such as C++ can give more domain-specific knowledge about the software. This can help enable parallelism. There are some problems with using OpenCL directly that could be addressed. One of these is data parallelism with limited task parallelism support. You can only access your data in buffers. As I mentioned previously, you have to explicitly move the data onto the host and pull the data off the host, onto the device, sorry, and pull the data off the device. And you have to understand these memory spaces that I mentioned as well. It can be very complicated to do that. So that's our reason for doing this. This is a very simple example of what we propose for our technology that we call offload CL. Offload for offloading onto the GPU, and CL for OpenCL. So this code is C++11 or C++OX, which is the next standard for C++. That enables functionality of C++ called a lambda function. Now, a lambda function is the black box that I've highlighted here, and everything within that black box is the lambda function and can be run on the GPU, given our technology. And what will actually happen is it will compile and generate an OpenCL kernel with that code. This lets you run OpenCL code without having to worry about the private memory space, the local memory space, or the global memory space. And all of the buffers here are set up for you with the ArrayView class that's on the code there as well. The way this works in the background is using, very simply, we have a keyword called offload parallel. And offload parallel runs on the GPU as an OpenCL kernel. If you compile this code with something that's not our technology, then what will actually happen is it will run it on the host, and it won't run it on the accelerator. This is provided simply by the preprocessor check there for ifdef offload C++. And it says standard C++ compilers will compile this section here, and everything else that's not standard will compile this section here. And when it does, the functor will be offloaded onto the GPU. This code here is taken from an example, a working example, that I'm unfortunately not able to show you today, but it's based on a seismic demonstration which simulates earthquakes and how earthquakes penetrate through various types of materials. It's been adapted from Intel's 3D building blocks, and I believe that the code is actually Intel's, and we have modified it to offload onto the GPU with OpenCL, and we also run it on CPU as well. So in the future, OpenCL could have task parallelization support in OpenCL 2.0. We don't know for sure though. We could change. There are some potential changes in the hardware model that could mean that in future revisions of OpenCL we could support shared memory spaces. This might eliminate the problems that you have with local, private and global being completely separate. As I mentioned, that is a very difficult thing for most OpenCL programmers or people who try OpenCL because it is a very new standard and there could be quite a lot of changes to it in the future and probably will be. One of the other things that the Khronos Group will be bringing to OpenCL in the future is a thing called HLM, which is High Level Model. And High Level Model is almost exactly what I've been talking about today, and that is the idea that rather than running OpenCL with a very separate memory space and kernels, it could run potentially within a C++ environment. But that's all very much being experimented with and debated within the Khronos Group meetings. So I've talked a little bit about Codeplay and the company I work for. So a very small overview of OpenCL and our offload CL technology, and a little bit of speculation on the future of OpenCL. That concludes my talk. Okay, thank you very much.
好，那今天上午我们的会议就到现在就是告一个段落。我们有在下边1层的子乐厅给大家准备了午餐，也请大家就一起在午餐上面，我们也可以就是进一步的再跟这些专家有就是更面对面的一个交流吧。然后午餐以后呢，我们有发给大家那个袋子里边有日程。午餐以后下午还有一些关于技术的介绍，然后也有一些关于我们有一个 CAT 项目，这个 CAT 项目呢是一个教育培训的项目，是针对。我觉得就是可能就是对一些就是在职的工程师也好，还是在校的一些大学生也好，都是就是比较有益的吧。然后大家也应该就是也可以下午再继续过来再听一下，了解一下。我们在 CAT 那个项目介绍之后，最后一个环节是一个讨论的环节，也是有今天早上我介绍的就是 Peddie 那个公司来的2位专家，然后会作为一个主持，然后我们一起有一个互动的一个环节，也希望到时候大家可以积极的参加到里边。然后我们的午餐是在1层的子乐厅，应该是差不多有1个小时的时间，我们可以1点10分左右结束，然后回到这边再继续下午的会议。好，谢谢。